Hello Science Alliance! Hello everyone, my name is Lara. This is iGCSE Physics for free, generally for home learners, but you might go to school and then watch up on catch up. Today we're doing impulse. I have to be totally honest with you, we've got some really good lessons coming up. We're just about to finish off forces and motion. In the next few lessons we're going to look at how things balance, we're going to look at centres of gravity, it's going to be a lot of interesting practicals. This is not one of those lessons, this is the lesson that I was kind of dreading, like, oh, we've got to get through it, but there's so much maths. I've actually really enjoyed it. Even just researching how to explain impulse and road safety to you, I've discovered new things about it that I really love. But just so you know what's in my heart, I did not enjoy physics at school, and we're going to be touching on some things that made me not like physics at school, so just stay with me, okay? And maybe you'll really enjoy it. Hopefully I will express my enjoyment to you in a way that my teacher did not. So let's have a look at what all these numbers, letters mean. Here we go. Wow, this is where we find out that my amazing PowerPoint display has not worked. And oh my goodness, oh, okay. So it's okay. I'll highlight them, and these words are supposed to be here. They weren't supposed to be hidden. Let's look at U first of all. What is U underlined in pink here? Well, U is the most confusing one because V and U are both velocity. But U is an object's velocity at the start, okay? It's initial velocity, and it's measured in meters per second. So, for example, oh, that's just my beautiful plant. For example, if you're sitting in a chair, then your velocity is 0 meters per second, yeah? Because you're not moving any distance per second. The V is also velocity, and that is how we describe the velocity at the end. Some of these equations square them, but don't be confused. V, the units for velocity is just a speed with a direction, isn't it? So the units for velocity are just meters per second. It's how many meters per second you are travelling. It's how fast you're going. Excuse me. So that's V, that crops up quite a lot. A is acceleration. Hopefully you know that acceleration, the unit for acceleration is meters per second squared. Meters per second squared means meters per second per second. So if you leap up from your chair and you end up over here running at, I don't know, wow, that is so, this is not someone running, doesn't matter. Running at 10 meters per second, then your velocity has changed, yeah? You've sped up, you've had a change of velocity. So we say that you've accelerated. Here you were going at 0 meters every second. Here you're travelling 10 meters every second that goes past. That's almost record breaking, isn't it? In the middle here, you were probably at some point going at 5 meters every second, but you've accelerated. Every second you've gone a bit faster, okay? So that's what acceleration is. That's where the squared comes in, meters per second per second. The S is displacement. Did you get that? It's very similar to distance, but it has a direction. We'll look a bit at displacement later on this lesson, but the S is displacement. It's just measured in meters. M is mass, measured in kilograms. That crops up in a couple of places. F is force, measured in newtons. And little p we did last week. That is momentum, measured in kilogram meters per second, which if you'd forgotten, you could have worked out, yeah? Because you just do the units of mass, which are kilograms, times the unit of velocity, which is meters per second. And when you times them together, it just looks like that. Kilogram meters per second. I did say that the units of force, the Newton, were made up of other units. Did you manage to work that out? Quite likely that you didn't. That's totally fine. I'm sort of touching on A level now. But if you know that F equals ma, right? The force at which you push something and its mass and its acceleration, like how they're connected, well, you know that force is measured in newtons, don't you? So you might be able to see that timesing the units of mass and acceleration together must give you the units of force, because it says that they're equal. So you could write the Newton, if you wanted to, as kilogram meters per second squared. Like I say, it's more A-level, but iGCSE physics does kind of brush up against A-level quite a lot. So I think that's useful to know, but it doesn't really matter if you haven't understood it just yet. Right, so yeah, we're going to look at how all these equations are connected and how equations make you think. So just very quickly, are you okay with the fact that if we're saying that u is your starting velocity and v is your final velocity, we've always written momentum as being little p equals mv, but you could write it as little p equals mu. That would just be describing someone's initial momentum, yeah? That would be their momentum at the start, and this would be their momentum at the end. Okay, so we can play around with these letters a little bit, yeah? In fact, we will play around with them just a little bit now, because I just want to show you something. This is algebra. Some of you are going to be pretty comfortable with algebra already, but just in case you're not, we can put these equations inside each other, yeah? We can have a little bit of fun. So a super simple example, just in case you haven't seen this before, a lot of you will have done. Here we have an equation, right? 3 times 2 equals 6. And here's another equation. 6 divided by 6 equals 1. This that I've circled is a 6. We are starting simple here, people. But this equation over here, 3 times 2 equals 6, well, we know that the 3 times 2 is also equal to 6. Yeah, so hopefully you can see that you can replace one with the other. We can stick 3 times 2 into this last equation in place of the 6, because they're both the same thing. So we end up with what looks like a new equation, right? 3 times 2 divided by 6 equals 6. Yeah? Okay, good. Right, let's do a little bit of something active. Let's throw a ball. I don't know if you would have a ball, so we're going to use scrunched up paper. Just get a few sheets of A4 paper and scrunch them up. If you've got scrap paper, if you've got a ball and you don't want to waste paper, you can use that. But I'm going to use this scrap paper. Get them really dense. Get those paper particles in the smallest space as you possibly can, so they're extremely dense. We're just going to have a think about what these equations actually mean. So, you've got your ball. Oh, I've got 2 balls, that's handy, so I don't want to have to get up. So, you've got a ball, you're going to throw it. What are you actually going to be doing when you throw the ball? Well, you're going to be taking its velocity from 0, because at the moment it's not moving any distance as time goes by, and eventually it is going to be moving, right? As time goes by. So you're going to be accelerating it. Is that okay? It's going to be going from 0 meters per second to some meters per second. So it's going to accelerate. It's going to speed up. When you apply a force. So if you throw it really gently, if you do not apply very much force, what's going to happen to the acceleration? Is it going to get faster? Is it going to end up really fast, or is it going to end up not very fast? Well, let's do it. Then it'll land on the table in front of me. Apply not very much force. Didn't go very far. Now apply big force. Whee! There you go. This is Newton's second law in action, yes? F equals ma. But it makes a lot more sense rearranged, really. A, acceleration, equals mass. Wait, no. Force divided by mass. There we go. So what you just did is you increased the force. So you increase the acceleration. What's going to happen if you change the mass of the ball? Don't do it, but imagine if you swapped out your little ball of paper for a bowling ball. What would happen? Well, you know what will happen, don't you? Because you live on the planet and you've experienced this kind of thing. But if you didn't know, you could look at the equation. Look, as mass gets bigger, the acceleration gets smaller. So if you were trying to hold like the moon and accelerate it, it would not work, because you wouldn't be able to apply enough force, right? M is too big, F is small, so acceleration is going to be very small. So we know this equation explains that quite well, yeah? Right. Put your ball down and just hold your hand as if you're throwing a ball, like, I don't know, some kind of weird claw action. Can you just extend your hand as far as you can, moving it at a constant speed? So I just want you to pretend you're holding a ball and just move your hand forward at a constant speed until, it gets to as far as it can go. Constant speed. What does that look like? What does that feel like? Constant speed, yeah? Now do it again, but accelerate your hand, okay? If you're just joining us, I don't want to be dismissive about the first part of the lesson, but you haven't missed very much. I haven't told you what impulse is yet, and impulse is the point of the lesson. Now accelerate your hand, yeah? What does that feel like? So your hand starts off slow and then it gets faster, right? It changes speed. It's going more. Which one of those feels more like a throw? Constant speed or acceleration? It's the acceleration, isn't it? The second one feels much more like you're throwing something. So hold your ball in your hand again. Let's think about what happens before you let go of the ball. Before you let go of the ball, you're still accelerating it, aren't you? Why is that important? Well, try throwing the ball without accelerating it. Like, don't even pull your fingers back. Just, you don't get as much acceleration, do you? This is why when people are throwing things in sports, they put the ball really far behind them, right? They hold it for a long time because, well, what is that doing? They're applying a force. They're accelerating the ball. They're applying a force to it. And you can feel, can't you, that the longer you're in contact with the ball, the longer you apply that force for, the further the ball is going to go. Let's try it. Just hold the ball back as far as you can, and then hold it for as long as you can, and then let go right at the end. So make it experience the force for a long time, see what happens. Ah, so satisfying. We got a higher acceleration, didn't we? But time is not in this equation, so we're going to have to use a different equation. Let me show you how all this fits together. Equations are not just plugging in numbers. Equations help us to see how nature behaves. I don't know why it's always YouTube that my phone holder goes wonky. Here we go. Equations help us to think, okay? So have a look at this one. We have got v, the velocity that it ends up as, is equal to its starting velocity, u, plus acceleration times time. Let's rearrange it. V minus u, final velocity, take away the starting velocity. What does that actually mean? We've just seen it. But what is it talking about? Well, can you see that the last velocity, take away the first velocity, that's a change in velocity of the thing. Yeah, hopefully you can see that. You know, we did about Hooke's law. Hooke's law, you look at the initial length of the spring, and then it extends, and you look at the final length of the spring, right? And to work out the extension, you do the final length, take away the original length, and that gives you the change in length. Yeah, so it's just the same thing. You run, and your final velocity, take away the velocity that you started with. That is your change in velocity. Is that okay? So v minus u is this change in velocity, times by what? How long a thing accelerates for? We're kind of getting to what we did with the ball, aren't we? Like, we accelerated it for a long time, and then the change in velocity was big. So let's put that equation up on the board again. This is where I start having flashbacks to physics lessons in the 90s, but don't worry, it'll be fine. Are you okay if I say that instead of v minus u, we'll just say this cute little triangle v? That means change in velocity. So it's the same as v minus u, but it's just a nicer way of saying it. So the change in velocity equals what? Acceleration times time. So we can rearrange this equation, right? So that acceleration is the subject. Change in velocity divided by time equals the acceleration of a thing. And we know that F equals ma, right? And if we rearrange that, we get F divided by m equals a. So we've got two things that are equaling acceleration, which we have looked at before, briefly. Are you okay with the fact that we can just take one of them and stick them in the other one, like we did with those simple numbers earlier? So we can say that change in velocity is equal to force divided by mass, right? Because they both equal a, so they both must equal the same thing. Are you still with me? This is what every physics lesson was like for me. The teacher would just write all these numbers on the board and then turn around and be like, do you see? And me and my friend would be like, every lesson. So this is where my heart starts pounding a bit. But I'm actually, believe it or not, I'm actually quite enjoying myself now. And the feedback is that you guys like algebra too, so it'll be fine. So here we go. Change in velocity divided by time equals F divided by m. Are you okay with the fact this is just cancelling we've done before? Times this side by m and put m up there to get F on its own. Times this side by t to get change in v on its own and put t up there. So we're going to swap those over. And we end up with this. Change in velocity times mass equals ft. This might look super weird, but it does still make sense if you think about what we were doing last week, okay? We learned about momentum last week. Momentum is mass times velocity. And look, we've got mass times velocity up here. So this is just momentum here. In fact, let's just change that round to make it look nicer. Look. Mass times change in velocity, that's momentum, equals ft. So last week, let's look at what this actually means in real life. We learned how this elephant is going to hurt more than a mouse going at the same velocity because it's harder to stop. And we said that this idea of unstoppability is called momentum, right? Mass times velocity. So it took me ages this, I hope you appreciate it. Here's a person stopping an elephant. When you stop the elephant, you change its momentum. Is that okay? So the momentum of the elephant is just mass times its velocity. So obviously, if you stop the elephant, you're changing its velocity. So you're changing its momentum. Okay. What you're actually doing to stop the elephant is you're applying a force over a certain amount of time. So if you apply, I mean, don't try this at home, but if you try to stop an elephant from moving, you will be applying quite a small force. So it will take you a long time to stop that elephant. It'll take a long time for the momentum to change. If, however, you get all your buddies, don't do it, but if the elephant charges you and all your friends, that would be a larger force, okay? You would be pushing back harder, so it would slow down faster. It would be less time for momentum to change. So here's the equation. This is what we're looking at. Ft equals mass times change in velocity. This is change in momentum. For a car's momentum to change from, I don't know, let's say the car's momentum is 10 kilogram meters per second, and then it changes to 0. You could apply a big force for a short time. Hope you're watching the screen. Again, this took me ages. Here's a car. It's got a lot of momentum, and then it suddenly changes to having no momentum very fast. You ready? Boosh. That was a big force being applied for a short time. Or, to change its momentum, you could apply a small force for a long time. Like if a car that you're not pushing on the accelerator runs onto some grass, right? There'd be a bit of friction from the grass, and eventually it would stop. But it would take a long time to stop. That would be a small force for a long time. Okay, everyone's still here. This is a good sign. So what Ft is, we know that m change in v is the thing's change in momentum. Say in this case it was from 10 to 0, so it'd be 10. Ft is called the impulse. We made it. If something's momentum changes, then it experiences an impulse, okay? Just like the elephant. Its momentum changed because it experienced a thing pushing on it for a certain amount of time. That is the impulse. The impulse makes the momentum change, and it's also equal to the change in momentum. This is where my head started exploding in the 90s. So, I'm just going to show you my face again, just because let's have a bit of human contact. I'm going to give you an example of a question, but this is, I mean, actually, if you're watching on YouTube, you might want to pause it and see how far you get. But really, this is an example so that I can show you the working, and then I'll give you an example that you can do yourself. So, V divided by T, that is impulse, yeah? M change in V, this is the change in momentum. So if something's momentum has changed, that's because a force has been applied over a certain amount of time. And this is what we did last week. Momentum equals mass times velocity. So a cat of mass 4 kilograms falls onto a sofa at 3 meters per second, and then it stops. Here's the kind of questions you might get. What is its change in momentum? You should be able to do that now, really. If you came to last week's lesson, you've been listening. How much impulse has it experienced? You might be able to do that too. And if it experiences a force of 6 newtons, how long did it take the cat to stop after it hit the sofa? So most people are going to be watching on catch-up. They might want to pause and go through this, or they might just want me to go through the answers with them so they can try the next question that's coming up in a second. But I'll give you 10 seconds to have a little think, because I think you should be able to do the first question in your head. And if you've understood everything I've said so far, then question 2 will be easy. And if you haven't understood, it will be hard. Okay, let's go through it. This is supposed to be the example. It's not supposed to be really you working it out. Right, the cat's mass is 4 kilograms and it was travelling at 3 meters per second, and then it stopped. Its change in momentum is, well, how its momentum has changed. So its momentum to start with before it stopped was little p equals mv. So you just plug the numbers in, right? Its mass times its velocity, which is 4 times 3, so you get 12 kilogram meters per second. If you did attempt this, give yourself a mark for 12 and give yourself a mark for kilogram meters per second, because 12 on its own isn't an answer, is it? It doesn't mean anything. I've been a bit lazy here. I don't think I've bothered to say the change in momentum, because obviously if it's stopped, then its velocity is 0, so it's just gone to 0. So its change in velocity is like 12 minus 0, which is still 12. How much impulse has it experienced? Can you see? I just accidentally opened an email from school. How much impulse has it experienced? Well, F times T, force times time, is the impulse. And we know that impulse is equal to something's change in momentum. You remember the elephant? For it to change momentum, it experienced an impulse, and the impulse it experiences is equal to its change in momentum. So if you've got the change in momentum, you know that the impulse is just the same. Okay? You worked out this side of the equation, so it's equal to that side of the equation. Same. If it experiences a force of 6 newtons, so if it boinks onto the sofa with a force of 6 newtons, how long is it going to take the cat to stop? Well, you know that Ft is equal to change in momentum, and you've just worked out the change in momentum, and they've given you F. It's 6. So you could just rearrange that equation because we're looking for the time. The time it takes the cat to stop is the change in momentum divided by the force, F. And we know that the change in momentum is 12 kilogram meters per second. And we know that the force is 6, so it's just 12 divided by 6, which is 2 kilogram meters per second per newton. Let's not worry too much about the units in this one. It's 2 seconds. The answer was 2 seconds. Well done if you got that. I didn't really mean for you to get that. That was just an example. Now I have some which I would like you to actually try. Yeah, so it's a lot of PowerPoint today, but I really have nothing else to say. Just come down and have a look at this. Here you go. Oh, you do have to look at the screen because there's a lot of real special effects in this worksheet. A bird is at rest, thinking about eating Theatre of Science mascot Wormy. No! She whacks it on the head. You ready? Boof. Again, it's just no expense spared with these effects. So a bird is at rest. It's thinking about eating Wormy, but she whacks it on the head. She's got a black belt in karate. If the bird's head has a mass of 0.5 kilograms, and the bird's head ends up moving away from Wormy at 6 meters per second, what was its change in momentum? And what impulse was delivered to the bird's head? The special effects aren't over, so stay tuned. If Wormy was in contact with the bird's head for 3 seconds, ready? Bam! Well done, Wormy. I will only eat seeds now. If Wormy was in contact with the bird's head for 3 seconds, how much force did she hit it with? And question 4, a trainee acrobat has a mass of 60 kilograms and travels at 3 meters per second. What is his momentum? Not a trick question. Question 5, he splats into a padded wall with a force of 45 newtons. How long does it take him to stop? And question 6, proud of this one. A ball hits a wall at 10 meters per second and bounces off at 6 meters per second. A cake hits a wall at 10 meters per second and sticks to it. Which one has the biggest change in velocity? Which one has the biggest change in velocity? I will do these with you, and then we'll go through them. If you're on to question 6, then I will tell you that the answer is the ball. The ball has the biggest change in velocity. So if you didn't get that, can you tell me why it's the ball and not the cake? Because that might seem a bit strange. Okay, what do you think? 20 seconds? Right. I have finished. And I was writing out all my units very carefully. So I'll go through it now. Don't worry if you haven't finished, there will be more opportunities to rearrange numbers like this, you lucky devils. So, jig the screen about. Check with my face for people who are on YouTube watching back. Hello, are you ready? I'm going to go through the answers now. Great. A bird is at rest, thinking about eating wormy. She whacks it on the head. The bird's head has been still, so it's had a momentum of 0 because its velocity has been 0. And then the bird's head starts moving at 6 meters per second, and it's got a mass of 0.5 kilograms. What was its change of momentum? Well, I've been a bit lazy, I suppose, really. I've just done the momentum is mass times velocity, so it's the mass of the bird's head times the speed the bird's head is travelling, which is 3 kilogram meters per second. If it was an exam, I suppose I'd really sort of have to say that its change in momentum was like that time minus 0, because which is like obviously the same thing, if you know what I mean. I don't want you. Yeah, you get what I mean, don't you? Because it was still, it wasn't moving. So the first momentum is 0. So the change in momentum is just the last momentum. What were the impulse delivered to the bird's head? Well, have you got this? Impulse is F times t, force times time. And that is equal to the change in momentum. So the impulse delivered to the bird's head is the same. Same, because Ft is impulse. Question 3. If Wormy was in contact with the bird's head for 3 seconds, how much force did she hit it with? All right, so then we do the whole equation. Force times time equals like the change in momentum, m times change in v. And we know that change in v is 3 kilogram meters per second, because I just worked that out. So we rearrange this equation because we're looking for the force, and say that force is change in momentum divided by time. And then just plug the numbers in, yeah? Because they gave us 3 seconds. So the force is 3 divided by 3, which is 1 Newton. Yeah, can you see how... Actually, no, it doesn't matter. Question number 4. A trainee acrobat has a mass of 60 kilograms and travels at 3 meters per second. What's his momentum? So that's not a trick question. His momentum is 60 times 3, which is 180 kilogram meters per second. Give yourself 1 mark for 180 and 1 mark for kilogram meters per second. 180 on its own is not an answer. It doesn't mean anything. He splats into a padded wall with a force of 45 newtons. How long does it take him to stop? So it's this equation again, but we're looking for the time. We're looking for how long it took him to stop. So we rearrange the equation so that change in momentum is on the top and force is on the bottom. So it's 180 kilogram meters per second divided by 45 newtons, which is 4 seconds. Well done if you got that. Let's do this cake ball question, okay? Did you get this right? If so, how did you get it right? If so, think about why it would be different if you were talking about displacement. So you've got a ball travelling at 10 meters per second, and it bounces off a wall at 6 meters per second. I told you the answer, didn't I? You've also got a cake, which was also travelling at 10 meters per second, but then it just splats into the wall and stays there. So it ends up at 0 meters per second. Which one had the biggest change in velocity? Well, I thought we should mention this. We're just going to touch on this because we need to do it a lot more later, and we haven't really talked properly about how you add up vectors. So velocity is a vector. It has a direction. So the answer is actually the ball has the biggest change in velocity, and the reason is you have to, if something's changing direction and you're talking about its velocity and you're doing the maths, you have to just pick a way that is positive and a way that is negative. It doesn't matter which way you pick. I mean, usually the ball's travelling towards the wall. So let's say that towards the wall is positive and away from the wall is negative. So actually, its velocity when it comes towards the wall is 10 meters per second, but its velocity when it goes away from the wall is minus 6 meters per second. So if you do its final velocity, take away its its first velocity, you're doing -6 minus 10, which ends up as minus 16 meters per second. If you haven't got this, isn't the last time I'm going to mention it, but I thought it's about time we dropped this into conversation. But the cake, it just goes from 10 meters per second to, so it's change in velocity. Oh, I've put minus. You don't need to put a minus, because obviously it's change in velocity. It can be a positive number. The cake's change in velocity is just 10 meters per second. Absolutely brilliant question from Alice when I did this lesson on Facebook this morning, who was like, yeah, but displacement is a vector, right? Displacement is distance, but with a direction. So, but I thought it wouldn't have a displacement because it's gone back to the same place. So why would the displacement be massive? Just very quickly, the difference with displacement is, because Alice was quite right, yeah, displacement is a vector. So let's say the ball bounces 3 meters this way and then bounces straight back to exactly the same place, another 3 meters. It's the distance that it's travelled, you just add up all the meters that it travelled, wouldn't you? So the distance in this case is 6 meters. It's travelled 6 meters. But for its displacement, you would also add up the distances, but you need to put the direction on. So you need to pick one of these to be 0 because it's going in the opposite direction. So you could say that at the top it's going 3 meters in the positive direction, and at the bottom it's going 3 meters in the negative direction. So you add those together and you end up with a displacement of 0. This is a massive tangent, but I just thought it was a very useful place to put it in. Is that all right? It's weird because you just choose which way is positive and which way is negative. You could say, okay, the top way is the negative direction and the bottom way is positive. But it still works out because you're adding -3 to +3, so you get an overall displacement of 0. Okay, anyway, thanks, Alice. Good tangent, helpful tangent. Right, I gave this lesson the absolutely fascinating clickbait title of Impulse and Road Safety. What has road safety got to do with impulse? Or, to phrase it another way, what has road safety got to do with impulse? Here's the equation for impulse. Ft, which is impulse, yeah? Just the force and the time that has to be applied to something to make it change its momentum. There's a big clue on the board. This person's delightfully frenzied eyes wearing a cycle helmet. What has road safety got to do with impulse? Remember the elephant. To change an elephant's momentum, you have to apply a force over a certain amount of time. You can apply a large force over not very much time, or you can apply a very small force over a long period of time. 10 seconds to think about that while I draw a picture on the board. Have a go. What has road safety got to do with impulse? What has impulse got to do with safety belts or baby car seats? I will tell you. Hello. Well, when you have how to make this like not really dark and awful. If a stone lands on your head, then what happens to that stone? It changes its momentum, right? It goes from moving at a velocity to not moving at any velocity. So if it hits your bare head, it probably changes its momentum very, very quickly, all right? It goes from, I don't know, let's say a momentum of 10 to a momentum of 0. And it maybe just takes like 1 second to do that because it's just hit your head and boosh, the momentum has changed. So the force is very big and the time it's taken for the momentum to change is very small. If you're wearing, say, a cycle helmet, then that cushions the fall. You remember like the cat landing on the sofa. If you've got a big cushion on your head and a stone falls on it, the stone will be changing its momentum much more slowly, okay? It'll just take more time to get to a momentum of 0. It'll take more time to stay still, if you like. So the force is less. Force and time are directly proportional, yeah? As one goes up, the other goes down. The change of momentum's the same. It's still gone from, I don't know, a momentum of 10 kilogram meters per second to 0 meters per second as it stays still on your head. But if you're wearing a cycle helmet or something, if you can increase the time it takes for its momentum to change, then you've decreased the force, which is good because it is the force that hurts you. Is that all right? Safety belts in cars are designed to be a little bit stretchy so that if the car suddenly slows down because it like crashes into a wall, you don't suddenly change your momentum. The seatbelt stretches a little bit, so it takes a little bit more time for you to stop. And because it takes more time for you to stop, then less force is experienced by your body. All right, I'm going to give you some practice questions. Here we go. These are for you to do. They're very similar to what we've just done, actually. Someone of mass 80 kilograms travels in a car at 56 miles per hour. That's 25 meters per second. How much momentum do they have? I haven't even given you the equation for momentum. We are over that now. 2 seconds later, the car comes to a stop. If the person does too, how much force have they experienced? And finally, an airbag is actually in the car, so it cushions the person. So they take 5 seconds to stop moving. What force do they experience? You got someone with a mass of 80 kilograms travelling at 56 miles per hour or 25 meters per second. How much momentum have they got? Hopefully pretty straightforward for you. If it takes them 2 seconds to stop, how much force have they experienced? And if there's an airbag in the car and it cushions the person so they take 5 seconds to stop, how does the force change that they've experienced? And once again, as usual, if you've got any comments or questions or grievances about this lesson, you can go to my Facebook page and there is a post up there saying, I'm on YouTube now, tell me what you think. So you can. Do these first though. Okay, I'm going to quickly draw a picture of a car on the board and then I'll go through the answers with you. There we go. Okay, let's go through the answers then. How much momentum do they have? Well, it's just 80 kilograms times 25 meters per second, isn't it? Momentum is mass times velocity, which is 80 kilograms times 25 meters per second, which is 2,000 kilogram meters per second. If the car stops in 2 seconds, or the person stops in 2 seconds, you've just got to rearrange this equation. So you've got 2,000 kilogram meters per second, which is the change in momentum. So you're looking for the force, right? So you've got to do force times time is change in momentum, and therefore the force equals the change in momentum divided by the time. We've already got the change in momentum, and they've just given you the time. It's 2 seconds. So it's just 2,000 divided by 2, which is 1,000 kilogram meters per second. Okay, that's quite a lot of force, isn't it? That's a lot of momentum, a lot of force, beg your pardon, 1,000 newtons. This is why I did that thing in the beginning where I showed you that newtons can also be expressed as kilogram meters per second squared, because you might look at that and think, oh no, I've definitely done something horribly wrong. But no, you haven't, it's fine. kilogram meters per second squared is just the same as newtons. An airbag is in the car. It cushions the person, so instead it takes them 5 seconds to stop moving. What force do they experience? Well, you can just change the time, can't you, for 5? Be careful, but can you definitely? Has anything else changed? Well, they've still got the same mass, haven't they? Their speed hasn't changed. The change in speed is the same, from 25 meters per second to 0. So this change in momentum is still absolutely fine. So yeah, let's just put 5 seconds in instead and do 2,000 divided by 5, which is 400 kilogram meters per 400 newtons. That's a huge difference, isn't it? It's taken 3 seconds longer for the person to stop, and it's reduced the amount of force experienced by them less than half. Well done, airbags. What a brilliant invention. So just finally, I'll show you this picture. Because you might have passed car accidents and seen cars looking like this, all crumpled up at the front, and think, oh no, that's awful. This is actually, I mean, maybe it was awful, but this is actually the car doing a really good job. This bit of the front is called a crumple zone. It's quite a new thing. All cars have crumple zones now, all over the place. Why is a crumple zone a good thing? Well, let's think about change of momentum. If you've got a car and it whacks into a tree and the car hasn't crumpled, then that car has probably changed momentum really quickly, hasn't it? It's gone from, I don't know, let's just say momentum of 10 to, I'll put the units in, kilogram meters per second, to a momentum of 0. Fast. This car, it's still had the same change in momentum, so it's been going at the same speed, okay? Wow, I'm supposed to say seconds. It's been going at the same velocity, and it's ended up at the same velocity, 0, but the time it took for that bit at the front to crumple has massively reduced the force on the people inside. So we can see this from the equation. Change in, I'm just going to put little p. Change in little p equals ft, all right? So if it's taken longer for the car to change its momentum, then time has gone up. So f has gone down. Does that make sense? The change in momentum is exactly the same in both cases. The velocity is the same, obviously the mass of the car hasn't changed, but because it's taken longer for its momentum to change, force is lower, right? Whereas in this situation, it very quickly changed its momentum, so force was bigger. Is that all right? Last question to check you've understood. Which car A or car B, which one has experienced the most impulse? Which one of those two vehicles has experienced the most impulse? There's no comments on this video, so I'm going to have to say we could be here for quite some time. I was getting a lot of different answers for this on Facebook. A lot of people saying that the crumpled car had experienced a greater impulse, yeah, because there's more force. Hopefully you can see that the impulse on the car is the same. Impulse is equal to change in momentum, change in m times v. And the change in momentum is the same, because what is momentum? It's the mass of the car, which hasn't changed, and it's the velocity of the car, which was the same in both cases. So these two are directly proportional, but the impulse is going to be the same. It's just that in one case f is high and t is low, and in one case f is low and t is high. Is that okay? Whew, okay. We got there. If you're watching this live, then I didn't give you any homework last week for our momentum lesson. But obviously there's an awful lot of momentum in what we've just done. So don't worry, I'll give you a mammoth bumper homework this week, and hopefully it'll all come out in the wash. And now you know about impulse, and you know about adding up directions, you can do loads of beautiful past paper iGCSE questions on this to test your understanding. All right, I'm going to go to my Facebook page and see if any of you have left me a message. You will know probably, this shouldn't be your first lesson really, but if it is, then you can support me by going to my About section on my YouTube channel and clicking the link to this website called Coffee. Adults, only you could do that. Children don't want you doing that. But yeah, I'm massively grateful for the support that I'm getting. This is actually my job. I can teach an iGCSE lesson every week during term time, and a home ed lesson like Lego Storytime, and an all ages home ed lesson. And I'll even send you Theatre of Science magazine. It comes out like roughly every 2 months. I'm frantically trying to smash together the Christmas issue, which is going to have like a Christmas tree spotting guide. You're going to be able to look at any tree and use your Christmas tree spotting guide to work out whether it's a Christmas tree. Very proud of it. It's going to have an enormous comic about the Christmas truce from World War I because I've researched it vigorously. But yeah, if you sign up now, I'll send you this one, which is the current one before that Christmas issue comes out. So it's on Times. It's got an article about Einstein's special theory of relativity. It's got to make your own sundial craft. It's got a beautiful comic about a family that sold time. It's got all kinds of things. Very proud of Theatre Science magazine. If you didn't know that Britain used to have different time zones, or where there's a clock that still shows you both those time zones, you can find out there. Thank you very much. Oh, hello, Eleanor. Oh no! Oh no, I've done it wrong. Oh, Eleanor, why didn't I read your comment ages ago? Oh no, that's so embarrassing. This lesson's usually on Facebook at this point. Oh no. Oh no. Oh, this is what you get when you're tired and panic at the last minute. It's because on Thursdays I do my homemade lesson at this time. Oh no! Everyone's going to think that I just didn't show up. Anyway, that's not your problem. You are actually watching this, so well done for coming. Oh, I thought there weren't that many people there. Oh, what am I going to do? I'll have to do tomorrow's. Right. I'll go and explain. Well done for working it out, you lot. Oh, that's so annoying. Okay. Thanks, guys. What do I do? Do I do this one on YouTube again? No, I can do this one on Facebook. Okay. I'll just go and explain myself. Oh, this is... I need to check my own timetable before I go live. All right, thanks for coming, you lot. I'll see you soon, somewhere. Bye.